want to welcome everybody here to Chem 51C. I feel like I need to address a source of confusion at the beginning of this lecture, and it's something that I feel is persistent for everybody who's taken organic chemistry here or at any institution based on the structure and way that organic chemistry is taught. And it has to do with the types of cations that you've been seeing since the very start of your organic chemistry course. There's three main classes of carbocations that are important for second row atoms that you've seen throughout our course here at Irvine and elsewhere. First of all, with carbon, there's carbocations. Everybody's familiar with carbocations. They're so important for SN1 and E1 reactions. Ammonium ions, you've started to see a few of those, such as when we do tin HCl reductions of nitro groups. We're going to have a whole chapter related to amines and protonation of amines. And finally, hydronium ions, which get a lot of airplay as being important for acid equilibria and pKa and titrations in general chemistry courses. And I want to try to help dispel a major source of confusion that's centered around these particular cation classes. Let's go ahead and think about what we expect these types of reactive species to do. So if you have a reactive species with carbon, like a carbocation, I think you know that if you take a hydroxide anion with a negative charge, it wants to attack that carbon. It's got a positive charge on there. You kind of expect that sort of a process based on your understanding of SN1 reactions. The carbocations like to be attacked. You know from general chemistry that H3O plus and hydroxide minus are in equilibrium with water. So water can deprotonate another water to generate hydroxide and hydronium, and then you can get the reverse reaction. We know that. We don't need anything special to learn that. That's general chemistry. But when we get to ammonium, it feels to me like maybe there's a source of confusion here about what will happen. Are we going to attack the N plus the way we do the carbocation, or are we going to deprotonate the way we do with a hydronium ion? Or if we have a double bond to an oxygen, do we attack the oxygen, or do we pull the proton off? Why is this so confusing, and why does it seem like there are different rules for these classes of carbocations? The reason why this is so confusing to you is, and I'm not sure if anyone ever told you this, is that there are actually two classes, two families of cations. So when we say carbocations, there's actually two different families. There are the ENIUMs and there are the ONIUMs, and they are as different as night and day. So when you say carbocation, you're actually not distinguishing between the ENIUM class and the ONIUM class. So let me introduce you to these two families of cations, because if you're not familiar with these, that's why you've been confused from day one in organic chemistry. Let's go ahead and start off by talking about ENIUMs. When you talk about carbocations, the word you should use when you describe those is carbonium ion. What that means is you have a carbon atom with only 6 electrons, 2 in each bond, 2, 4, 6, and an MTP orbital. 6 electrons. Of course, that wants to be attacked by nucleophiles. Carbon wants 8 electrons. But there's another related species that you haven't seen, and that's a nitrenium ion. It could be called an aminium ion. I'm not sure of the IUPAC nomenclature. And that also would have an MTP orbital. And it would also have only 6 electrons. And if carbon wants to be attacked, nitrogen with 6 electrons would be desperate to be attacked by something. It wants 8 electrons, even more than that carbon atom does. And finally, with an oxygen atom, there's a corresponding species called an oxenium ion, which would have an MTP orbital and only 6 electrons. These 6 electron species are desperate for an extra pair of electrons. They will be attacked by anything. They're so unstable. But let me roll over here to a different class of cations, the ONIUM family. And when we look at the ONIUM family, I'll start down here with oxygen. I think we all know that hydronium, that oxygen can have 3 bonds and a positive charge. That's H3O plus. And you've known about that probably since the very first chemistry class you ever took in high school or wherever you took your first chemistry class. If you take ammonia and you protonate it, you get an ammonium ion. Stick a proton. Everybody knows ammonium is a common species. That's also a general chemistry topic. What you have not heard of before is this species called a carbonium ion. when you stick a proton on a methyl group, you'll end up with a species that ends up with 5 bonds to carbon. And if that looks strange to you, or if it looks like it violates some rule that you may have mislearned sometime in the past, then we need to talk about that in more detail. Okay, let's try to think about these reactions of ENIUM ions and ONIUM ions. How would you generate those conceptually? Conceptually, if I took methane and made hydride anion act as a leaving group, if I gave the electrons in this CH bond to the hydrogen and lost hydride, that would generate a carbonium ion. And similarly, if I took ammonia and used a hydrido, this would never happen, a hydride as a leaving group, you'd end up with a nitrenium ion. And similarly, the way to think about generation of a positively charged oxenium ion would be to lose a hydrido group from a water molecule. So, all of these you can think of as being derived from the parent compound through loss of a hydrido group. Now, when we think about the ONIUM family of compounds, I feel like that's a lot simpler. You take water, it's got lone pairs, you attack a proton or a proton source, and you get an oxonium ion. Right? This oxonium is the general class of molecules that hydronium fits in. If you take ammonia and you protonate the ammonia using the lone pair, you'll get an ammonium ion. Now, what's odd for you to think about is what happens if I take a methane molecule or some alkane molecule with nothing but sigma bonds and no lone pairs, and I attack a proton. I don't have any lone pairs in this molecule, so I'm going to have to use the 2 electrons in one of these CH bonds. So once I take those 2 electrons and I attack H+, 2 of those CHs are going to be sharing 1 pair of electrons. So overall, when you look at this molecule, it may seem to violate your senses, but it still only has 8 electrons. I haven't added any additional electrons to this molecule. And as long as you don't violate the octet rule, you're okay. The problem with 5 bonds to carbon is if you don't write a positive charge. That can't exist. The octet rule is inviolate for second row atoms. You can't go above 8 electrons there. So get comfortable with that, even if you're not comfortable with those carbonium ions. Now, why haven't you heard of these before? How come nobody told you that there were 2 classes of cations, ENIUM family and the ONIUM family? Well, it is so hard to generate carbonium ions, these types of carbocations that have an empty lone pair, that when you go to more electronegative atoms like nitrogen or oxygen, that is just completely out of the question. You have never seen a nitrenium ion or an oxenium ion. You never will see a nitrenium ion or an oxenium ion. They don't form, they don't exist, don't talk about them, so they're completely conceptual. So maybe they were right to just forget about those and not mention them and pretend there's no way to even talk about their existence. So I think they were kind of right to leave these out. So now it seems kind of like you were left to only consider one type of carbocations, carbenium ions, and then these 2 types from the ONIUM family, oxonium and ammonium, and they are completely different from carbenium ions. But I want to talk about this last one, carbonium ions. That one should look strange to you. Why didn't they talk about that before? Did they give you some rule that said you can't ever have 5 bonds to carbon? Maybe 5 depicted bonds would be a fair description. Let's go ahead and look in detail about where you've seen these types of species before. I think you've all seen generation of carbenium ions before. You have a leaving group attached to carbon, it leaves, and it generates a carbenium ion, which is one of the 2 types of carbocations. But let's go ahead and back to this idea of using the electrons in a carbon R bond or a carbon H bond and using those electrons to attack a proton. You're not adding any electrons. The carbonium ion carbon here doesn't have more than 8 electrons. It still has only 8 electrons. Is there something that is so acidic that it could donate a proton to an alkane? The answer is yes. I'm going to show you how you generate an acid that is so acidic. It turns out that antimony pentafluoride is so unbelievably, SB is antimony, is so unbelievably fluoride loving that it will add to HF using the lone pair of the fluorine atom. And so you'll generate this SbF6 species that just loves having that bond to fluorine. Fluorine just loves being bonded to antimony. But the problem is it's still got this proton stuck to it. and a positive charge on fluorine, and it is not happy. It will do anything to get rid of this proton, anything at all, even if that means donating the proton to an alkane. This is referred to as a superacid. It's 100 billion times stronger than sulfuric acid, and it is so strong that at high temperature, it can donate protons to alkanes. And you may say, well, that's completely fictional. When am I ever going to see that? All the time. Every time you've driven down the 405 freeway near LA, you pass by, just after you pass by Long Beach, you pass by these refineries, kind of in the Torrance area. And when deep inside these refineries, they're taking crude oil, petroleum, and they're exposing them at high temperature to these types of superacids. Those superacids are protonating in alkanes. And when you protonate an alkane to give a carbonium ion like this, they fragment. This carbon with the plus is not happy, and it can take the electrons from one of the carbon-carbon bonds in order to generate an alkane and then a carbocation. And that splits the long alkane chain in two. So you take long alkanes in petroleum and you crack them into smaller alkanes, like gasoline. This is where all the gasoline comes from that is in your cars. They're using carbonium ion cracking in order to generate shorter fragments, shorter alkanes. And then they distill them out using these super tall fractionation columns in order to harvest, the lower molecular weight, more volatile species that have different applications. So there's two classes of cations, two families of cations. There's the ENIUMs, and then there's the ONIUMs. And you've never really talked about before these carbonium ions. You've only talked about carbenium ions. And unfortunately, you've probably used the word carbocation and thought that there was only one type of carbocation. But now you've learned about the second class. Okay, let's go ahead and get on to chapter 21. That's really the meat of our lecture here. So I'm gonna have to stop and turn on my document camera. All right, the meat of our lecture today is we're going to talk more about carbonyls, but in this chapter, in this section of the course, we're talking about not super strong carbon-carbon bond forming or hydride carbon bond forming reactions, but weaker classes of nucleophiles. This is actually, the chapter is kind of a hodgepodge of different nucleophiles, as was the last chapter in a way. So I want to stop and talk more about the reactivity of carbonyls, because the reagents in this chapter will be a lot choosier with what types of carbonyls they react with. So let me start off by, I want to compare different types of carbonyl compounds that don't have heteroatoms, aldehydes and ketones. And the best way for us to understand aldehydes and ketones is to compare the corresponding carbocations, carbenium ions, with our new language here, in terms of their reactivity. I hope everybody knows here that primary carbocations are extremely unstable. Extremely unstable. They tend to do hydride shifts to generate secondary and tertiary carbocations that are more stable. Secondary carbocations with just one extra substituent are more stable. And the reason that they're stable is because the electrons in these neighboring CH bonds are donating electron density into those empty p orbitals. And that helps to stabilize that carbocation and make it less reactive. And then finally, you get to tertiary carbocations that have three alkyl groups or aryl groups next to them. And again, if these have CHs or CC, if these have bonds on the neighboring atoms, those bonds can donate into that empty p orbital and help to stabilize that. Generally, when you have more stabilized carbocations, like tertiary carbocations, they will also be more hindered. And overall, because of that donation that stabilizes them and because of the steric hindrance, they end up being less reactive than primary carbocations. Now, generally, all carbocations, all carbenium ions react so quickly that you don't really worry about those differences in rates much. But when we come to these carbonyl derivatives, we're going to see the same types of effects. Carbonyl compounds you can think of as being just like carbocations. I can draw a resonance structure for these that makes this carbon atom look like a carbenium ion, and it's got an O- substituent on it. So these are all kind of like carbenium ions. And the more alkyl groups we have on these carbonyl carbons, the more stable they are, the less reactive they are. So we're going to see that ketones are less reactive than aldehydes, just as tertiary carbocations are less reactive than secondary. And aldehydes are less reactive than formaldehyde. Formaldehyde is so unbelievably reactive. I'm not sure that you're ever going to see or do or see reactions of formaldehyde. It doesn't normally exist like this, except in the gas phase. It reacts with itself. It's so unbelievably reactive and hard to work with. Okay, so this chapter is totally about aldehydes and ketones and things that they can do other than react with Grignard reagents. The book always seems to start every chapter talking about IUPAC nomenclature. And I think I took all the IUPAC questions off of my homework, off of the problem sets that are in Sapling. So if I left any on there by accident, sorry about that. But it's just that I don't expect you to memorize IUPAC naming systems. I don't think that's reasonable. If I gave you this long molecule down here at the bottom, you would probably recognize this as being acetyl-CoA. I don't care about the whole IUPAC name for this. The only thing I care about this is that it has an acyl group attached to a sulfur. That's the only significant part of this molecule, at least for chemical reactivity. So I would hope you would know that this is a thioester. And that's typically the way chemists roll. We don't talk about IUPAC nomenclature. We talk about the names of functional groups. So what functional groups do I expect you to know if I ask questions on an exam? I don't expect you to know full IUPAC names. Here's one of the first and most important functional groups. And we've already talked about these when we talk about acyl chlorides. So this type of group right here, where you have R being methyl, ethyl, alkyl, phenyl, we refer to this as an acyl group. That whole thing attached to whatever the X is, doesn't matter what the X is. It can be a benzene ring, can be a nitrogen atom, can be an oxygen atom. This group over here on the left-hand side, we refer to that as an acyl group. And there's many different types of acyl groups, but I'm going to give you two in particular where I expect you to know the names of those acyl groups because there's two super common ones. And you've seen them before, you've been seeing them throughout the Chemistry 51 series. The first one is when the R group is a methyl group. This is so common. This is the piece you have on acetic acid, on acetone, on acetamide, and this is referred to as an acetyl group. It's a very particular type of acyl group. And I expect you to know that name. If I refer to an acetyl derivative like acetyl-CoA, then I expect you to know where's the acetyl group in here. There's only one acetyl group, and that's at the very end of that molecule. So you need to know this. The name of this thing here, which is the acetyl group. There's another acyl group that I expect you to know the name of that is so common that you just need to know the name. And that's when there's a phenyl substituent attached to the carbonyl. This group that I've drawn right here is referred to as a benzoyl group. And it can have a phenyl group on the other side, but this part that I'm outlining with a box, that section of the molecule is referred to as a benzoyl group, like benzoic acid, benzoyl, benzoyl. And that's a benzoyl group. I think I meant to cover that in red. Okay, so you need to know the names acetyl and benzoyl. They're so common, right? If you're going to memorize the name of two acyl groups that are useful, then those are the ones you need to know. Now, there's a section in the book that talks about physical properties of aldehydes and ketones. Zero chance I'm going to ask you anything from that section. That would just be rote memorization that you really can't use for an exam other than to give. That's not, so okay, go ahead and skim it, but I'm not going to ask you anything from that section on memorizing boiling points or any of those typical properties. Okay, what am I likely to ask you about? I'm not going to ever tell you what's going to be on my exams, but I don't think I would tell you exactly what's going to be, but I usually put a spectroscopy question on each of my exams. Spectroscopy is important. It's the basis for so many fields of science and technology. I expect you to understand how those work. So coming back over here to this, to the types of spectroscopy that I give you, I usually give one of two types of spectroscopy problems. One kind of spectroscopy problem, I would give you just a series of compounds and say, which one of these fits the data? The other type of question that I would ask, maybe I'll give you a starting material and a whole bunch of steps and say, okay, what's the product? And usually I try to make the steps so complex that you have to use the spectroscopy to figure out what's there. So how do you use spectroscopy to answer questions? The kinds of questions that you confront in a laboratory, the kinds of questions you find in my exam. Usually you don't find the right answer. What you do is you eliminate the wrong answers. That's usually what spectroscopy is useful for. And my recommendation to you is when you're confronted with a spectroscopy problem, use the easiest data first. So let's talk about that. Let's organize spectroscopic information by ease of use. We don't talk in this class about mass spectrometry. Mass spectrometry is powerful for giving you molecular formulae. So if I give you a molecular formula, use it. That's the easiest piece of information for you to use. Anybody can use the molecular formula to rule out compounds. If I tell you there's a compound that has a molecular formula C5H7NO2, before you look at any of the spectra, why don't you rule out the compounds that don't fit that formula? So I see a bromine over here. Write out. Bye. I see something over here, the chlorine and a bromine. That doesn't fit the formula. I see a molecule over here that has no oxygen atoms. That's not, I mean, we've already cut out half of the possibilities just by using the molecular formula. And you didn't need to know any real spectroscopy to do that. And I haven't checked the hydrogen count here. Some of these, or here's something that only has one oxygen, and I told you it has two. We can even further rule out stuff. So we're kind of down to two types of compounds there just by using the molecular formula. Sometimes you'll have more left. So use the molecular formula. It's easy to use. I feel like you ought to be able to do that. Okay, what's the next easiest piece of information to use? It's the C13 data, the carbon-13. Usually the number of peaks in your carbon-13 spectrum should equal the number of carbon atoms in your molecule, except for the issue of symmetry. Remember that if you have symmetrical molecules or symmetrical functional groups, sometimes because carbons are indistinguishable, you'll end up with fewer peaks than the number of carbons in the molecule. So for example, if you have an isopropyl group on an achiral molecule, those two methyl groups are indistinguishable. You won't see 3 peaks for this isopropyl group. You would only see 2 because the CH3 groups are indistinguishable. So watch for symmetry. But it's so easy to just count the carbons. And I'll show you in a little bit how to use those chemical shift ranges. Next easiest thing, because it's so pathetic and has so little information, is infrared spectroscopy. So there's a few functional groups that you can identify using infrared spectroscopy, IR spectroscopy. You know, you can't ever just show somebody an IR spectrum and they say, oh, I know what that molecule is. That's not possible. All you can do is say, oh, there's a ketone, or oh, there's a CH bond. So what can you find in an IR spectrum? So for example, when I look at this IR spectrum, I see there's a big strong peak, 1800 to 1700. That's a carbonyl group. Okay, I know there's a carbonyl. Of course, I already knew there was a carbonyl from the C13 spectrum. I'll talk about that shortly. What's weird is I see this peak in this 2000s region. Boy, it is rare to see anything there. That's like the Mojave Desert. You know, there's usually nothing in this region around 2000 down to 1800. If you see stuff down in that region, or 2500, there's a triple bond. I mean, there's an sp hybridized carbon that's almost always a triple bond. So I see things here that had triple bonds that we ruled out for other regions, but you know, I'm coming down to the fact that I see a nitrile here. That CN group is a CN triple bond. Here's another one. So I can't really use that. At least it's consistent with these structures that I haven't ruled out yet, but I don't get any extra information. Both of those possible structures have CN triple bonds in them. And then finally, I look over here at the IR, and I draw an imaginary line at around 3000. Usually I just hold a straight edge piece of paper there. And if you have peaks that are greater than 3000 wave numbers, you know, in this CH region, just on the other side of 3000, that implies that they're attached to sp2 or sp hybridized carbons. But this tells me that everything's attached to a sp3. Because it's lower than 3000 and nothing is above 3000, that means all the CHs are sp3 hybridized. I don't have any H's attached to CC double bonds. So, and this peak is nowhere near big enough. That's just a little bit of water in the sample. Water absorbs so strongly you'd see a big blob from hydrogen bonding to OH groups. Okay, so I can learn about a few functional groups from IR spectroscopy. I can tell if there's a carbonyl group there. I can tell if there's CH bonds and maybe get a little bit of information about the type of CH bond. And I can see if there's triple bonds. That's not a lot of information to get. The last thing that I would use is proton NMR. And when you look at proton NMR data, let me suggest that you just skip the splitting and go right to the integrations. What you care about is, are they CH2 groups? Right? You're trying to figure out, are there CH groups, CH2 groups, or CH3 groups? And usually you get that type of information from the integration, how many H's. So I see down here, there's a triplet with 3H. You know, when I see something with 3H, it's usually a CH3. That's not because of the T, but because of the 3H. When I see a singlet with 2H, forget the singlet. I see 2H, that suggests that there's a CH2 group. And then come over here and I see a quartet with 2H. Forget the quartet, it's a 2H. That's probably a CH2 group. Doesn't always have to be that way, but that's usually the way it breaks down. So, right, I look at those, and what molecules fit this pattern where there's two CH2 groups and a CH3 group? Well, unfortunately, I see here, there's a CH2 and a CH2, and over here, there's a CH2 and a CH2, and they both have one, so I can't even use the integrations in this particular case to rule out which of those two molecules is right. Finally, I'll end up coming down here and looking at splitting. That's the hardest type of information to use. And it turns out that if I see that one of these has a quartet with 2H, that tells me it has to be next to a CH3 group. There's only one pair of hydrogens here that is next to a CH3, and that's this one, and this is the quartet. And you may get the splitting from some of these others, like this one over here has a 3-proton singlet that doesn't get split by anything. And right, I don't see over here a 3-proton singlet. So again, this has to be the structure of the molecule. So this is an unusual case where you can't figure it out until you finally get to the splitting. Usually you can figure it out, sometimes with just one spectrum, maybe just the C13 or the IR. But again, the goal with spectroscopy is to rule out plausible structures. So if I didn't give you any plausible structures, you need to write some out on your own and start ruling out some of the ones until you narrow things down. Okay, so spectroscopy. Let me go ahead and continue a little bit and talk about carbon-13, because it's a pretty useful type of spectroscopy. Over here and check my camera for a second, because it looks like it's not showing my, not that that really matters. I've turned off my video for some reason. I don't even know what's going on with that. Not that you need to see my face to see it's the chemistry that's important. There we go. Oh, wow. Doesn't allow me to adjust the, okay, whatever. It doesn't allow me to go to full width on the, there's actually a control setting that allows me to fill up this screen, but it's not working right now. I don't have time to work that out. Let's talk about carbon-13 spectroscopy, because carbon-13 is much easier to use than proton NMR because there are chemical shift ranges with C13. So for example, when I look, if I want to know whether things fit with this molecule called estrone, it's related to estradiol, one of the steroid hormones. It's important to humans. What are the functional groups I would expect to see in the carbon-13 NMR? What's great about carbon-13 is it's got defined ranges that are mostly separate. Not totally separate, but mostly separate. And when I look down here at this region past about 190, this is where you find ketones and aldehydes. That's great. The ability to tell the difference between a ketone and aldehyde versus stuff with heteroatoms attached is awesome. So this can be R or H, so an alkyl group. Down past about 190, that's great, it's separated. Now if I have other types of carbonyl groups that are attached to heteroatoms, that could be oxygen, could be nitrogen, right? The oxygen, nitrogen, even a chloride, that's not very common for you to isolate an acid chloride. Those are appearing down here from about 190 to about 155, maybe I'll say 185 to 155 here in this region, whereas this is greater than 185 in this region over here. You know, there's kind of an annoying overlap with this other region of the spectrum, but it's great that you can usually tell the difference between an amide and an aldehyde, or an ester and a ketone. And so, of course, for a typical ketone, look how far downfield that is. It's way at 220 parts per million for a ketone, right? You'll never mistake that for a carboxylic acid derivative or an ester. Okay, in this region up to about 160, so maybe from about 160 to 110 parts per million, this is CC double bonds in 160 to 110 parts per million. Now, you can't know whether that's CC double bonds that are parts of benzene rings or just plain alkenes. Unfortunately, they're all kind of in that region. You know, when I look at the structure of this estrone molecule and I count the number of different CC double bonded carbons, 1, 2, 3, 4, 5, 6, sure is satisfying that there's 6 peaks here in this region of the spectrum that corresponds to CC double bonds. A lot of times you'll have symmetrical benzene rings that where one side is symmetrical with the other, and you'll see fewer than 6. That's a pretty common situation to have some symmetry in your benzene rings. When we get down below here, this is all the junk that's attached to 4 different atoms. Doesn't matter whether it's chlorine, hydrogen, oxygen, 4 different atoms, sp3 hybridized, it's all down here. Don't try to sort out what's attached to that. You can't really do that. So you're not going to be able to tell whether there's an oxygen attached or a chlorine attached just by looking at the chemical shift. You just count the carbons and make sure it matches. I'm not going to take the time to count up the carbons here, but you know, the number of carbons that have 4 bonds attached to them is going to equal the number of peaks down in that part of the spectrum. So because the regions of C13 are distinctive, that's what makes it usable, user-friendly. And try to take advantage of C13 spectroscopic information when you get it. All right, let's go ahead and talk about review. That's kind of good when the main stuff you're supposed to learn in the chapter is just a review of stuff you already learned, because you're not actually getting new material, you're just reinforcing old material. Let me show you some of the things. There's a section here in this section of the book where it's a review of all the ways you know to synthesize aldehydes. And you need to know how to synthesize aldehydes, because every time you get an aldehyde, you should be thinking, man, I want to add a nucleophile to that aldehyde. Carbonyls, carbonyl chemistry is about adding nucleophiles to carbonyls. That's what carbonyl chemistry is. So know how to make aldehydes and ketones. Let's talk about aldehydes first. So way back in this section on oxidation and reduction reactions, you learned about chromium oxidants. And probably the most useful chromium oxidant by far, no question, is PCC, pyridinium chlorochromate. You don't need to know that that stands for pyridinium chlorochromate. This is the only way you can do this transformation efficiently, to take a primary alcohol with a CH2 group next to an OH and convert it into an aldehyde is using PCC. So you need to remember that. And then I hope you're thinking that all the ways that you can add alkylithiums and organomagnesium compounds to that. So another reaction that you learned about in the last chapter, where we learned about these hydrido-reducing agents. We talked about lithium aluminum hydride and sodium borohydride, but there's one reagent I don't want you to forget, and that's for reducing aldehydes, or reducing esters to aldehydes. And that's dival H, step 1, and then aqueous workup, step 2. And you need to remember that aqueous workup. You have to remember that. I'll write the word workup there, because I don't want you to think I'm trying to do SN2 chemistry or some other thing by adding water. I'm just trying to protonate all the junky molecules and get rid of them in this particular case. You also, in these reactions, generate a leaving group like this, but usually it's methyl ester and you're getting rid of methanol, or ethyl ester and you're getting rid of ethanol, and you evaporate those off. But you do generate the alcohol byproduct with these conditions. But usually you're trying to get rid of that when you use dival H. Not always. Okay, way back in the alkynes chapter. Man, this is like ancient history for you now. You learned how to do hydroboration oxidation reactions, the same hydroboration oxidation reactions that you learned for alkenes, but when you apply them to an alkyne, they don't generate an OH and an H on an alkene. They generate an aldehyde. And we'll make more sense of that in a couple of chapters when we start talking about a species called enols. Don't worry about the mechanism or the intermediates in this reaction, but I want you to know this transformation. If you take a terminal alkyne, you can convert that into an aldehyde. So the steps are hydroboration with borane, BH3, followed by the hydrogen peroxide workup, and it's base and hydrogen peroxide. And these reagents may seem kind of complex to memorize, but you have to memorize them. Hydrogen peroxide and sodium hydroxide. And you have to remember both of those. They're both part of that workup that you need for the, I kind of seem to have lost my camera again, so I'm not quite sure what's going on with that. Okay, let's go ahead and talk about the last type of reaction. It's the oxidative cleavage of double bonds. And if you have hydrogens on your double bonds, let me go ahead and put them in a different color here, then those hydrogens will lead to aldehydes on your cleaved products. This is an ozonolysis reaction, and it's another two-step sequence here. Step one, ozone. You pass oxygen gas through an electric arc, it generates ozone, you bubble that into your reaction, and it cleaves and makes some dangerous peroxides that we don't ever draw, and we don't talk about the mechanism for those. So you need to follow this with a workup to reduce the peroxides to something safe, and what we use is dimethyl sulfide. I'm not sure, some people write the letters DMS. It's like an ether, but it has sulfur instead of oxygen. And the sulfur lone pairs do chemistry in this reaction. You don't need to know about the mechanism for this. You just need to know that you can take an alkene and split it with ozone. Usually not benzene rings, but simple alkenes. Let me go ahead and come back to the, okay. So you need to know how to make aldehydes. You know, you also need to know how to make ketones, and generally that's very, very similar. This idea that you can make ketones out of alcohols or by hydroboration oxidation. Let's talk about those sequences. Okay, ketones. Again, some of this is kind of similar. So when I see an alcohol and I want to convert it to a carbonyl compound, where it's really an OH, PCC is the easiest thing to remember because you don't have to worry about the mechanism. They didn't talk about that. PCC oxidation. Well, what could be similar? It's the same reagent that you used to convert primary alcohols. But if you have a secondary alcohol and you treat that with PCC, you get a ketone out of it. Now there's another reagent that you can use in this instance, and it's the same reagent that converts primary alcohol, oops, it should be CrO3, chromium trioxide, with sulfuric acid and water. And it's the water that, that really makes this a distinctive reagent. You know, that's a lot of stuff to memorize. I don't know about you, I'd rather just memorize PCC. But you do need to use this reagent to convert, let me go ahead and write it in blue here so it's distinctive. This is the reagent system that you use if you want to convert a primary alcohol all the way to a carboxylic acid in one step. And it's the water that makes that happen. You never do PCC in water, because if you're going to do PCC in water, you might as well use inexpensive chromium trioxide to do that chemistry. Let me try to, I feel like I keep fiddling around with my camera here, and I apologize for that. Wow, I guess that's the camera I'm going to have here for the, give me a second. Okay, it's my external camera has sort of died here, so I'm gonna try to turn this around so I can get the camera facing me a little bit better here. Uh-oh, you're getting a sense for all of my contraptions. Okay, let's keep going on the synthesis of the carbonyl derivatives. The other way to make ketones is something that you learned in the last chapter in electrophilic aromatic substitution. You do Friedel-Crafts acylation and it gives you ketones. We don't have any version of this reaction that you learned about that allows you to generate aldehydes. So you already know I hope you already know the reagent and have been practicing with it. When you take an acyl chloride and aluminum trichloride and a benzene ring, it can't be a deactivated benzene ring, or it can't be an aniline, or it can't be a a benzene ring with a meta director on there. And those allow you to put attach carbonyl groups to benzene rings. We still have this opportunity to do ozonolysis reactions. And again, if one of the carbons in your alkene has two alkanes on it, you're going to get a ketone as a product in that reaction. So this is really the same reaction sequence if you want to generate aldehydes. In this particular case, one half of the molecule generates an aldehyde, and then the top half generates a ketone. So the sequence is ozone, step 1. And then step 2, in this case, is you follow this up with a dimethyl sulfide workup. So here's dimethyl sulfide. Again, some chemists abbreviate that DMS. So if that's what you want to do, then that's, but I would prefer that you write out something to indicate you know the chemical structure. Boy, the last set of reagents for this reaction. I'm kind of regret showing this to you. This was in the last chapter. They showed you, we talked about using cuprates to do conjugate additions, 1,4 additions to alpha beta unsaturated carbonyl compounds. And you can use those same cuprates that we learned about to add to alpha beta unsaturated carbonyl compounds to substitute chlorine groups from acyl chlorides. And you have to follow this up with an H2O workup to get rid of some of the junky species in there. I've never heard of any organic chemist that would take a valuable acid chloride and do this stupid reaction with that. I don't think anybody's done this except for a synthetic curiosity. And, you know, the book talks about it. I can't think of any conceivable circumstance where I would ask you about that useless, worthless reaction. So I'm not going to tell you, I can't promise it's not on our problem sets. I can promise you I would never put that on my exam. It's kind of a worthless reaction. Okay, in this chapter, we're really talking about a lot of conceptual stuff. And so we need to get to conceptually what this chapter is about. So let me start off by reminding you of what the last chapter was about. The last chapter was about taking super powerful carbonyl reacting compounds like alkyl lithiums and adding them to carbonyl groups. And you don't need to do anything special. If there is any carbonyl group anywhere in the city of Irvine, California, or the state of California, this bond is going to attack that without any problem whatsoever. You can't stop that from happening. That addition step is so fast. Mechanistically, we refer to that as addition, that step. It's so fast you can't stop it. Nothing can stop that reaction from the methyllithium from adding if there's a carbonyl there. And there we go. That was the big theme. And then I already told you that chemists don't like to isolate alkoxide salts, sodium alkoxides, lithium alkoxides. We don't want to do that. We want neutral molecules. So we followed these with an H2O workup. And I tried to explain to you why we never, ever, ever put water in with our alkylithiums. Remember that tert-butyllithium video where it bursts into flames just by coming into contact with the water molecules in the air. So we always, as a second step, step 2, that's when we add the water workup. We never put those together in the same reaction. We don't put an alkylithium and water in the same reactions or any OH compounds. In this chapter, we're going to learn about a different class of nucleophiles. Actually, multiple different, but one particular class of nucleophiles we're going to learn about is so weak and so pathetic that we need to give it some help. And that's oxygen nucleophiles. Oxygen nucleophiles, like alcohols or water. In these cases, we have to add an acid to these reactions to get the oxygen lone pairs to be able to react with that carbonyl. So we put an acid into these reactions, and then there's this acid-base equilibrium. So oxygen pick up a proton, take it back, pick up a proton, take it back, pick up a proton, take it back. Every once in a while, the carbonyl oxygen will pick up a proton, and then it'll give it back. It's all in equilibrium, back and forth, protonate, deprotonate. But every once in a while, when you've got this carbonyl protonated. This is now way, way, way more reactive than any normal carbonyl that's comparable. This is now so reactive that that pathetic oxygen nucleophile can now attack that. And this is the secret to getting oxygen nucleophiles to attack carbonyls, is you have to include an acid. And in this case, you don't worry about the acid reacting away all the alcohols. It's, you know, it's hard to protonate an alcohol. Whereas there's no way you could have any acid, any OH present with an alkyl lithium, because that would immediately react with the alkyl lithium and it would be game over. So not only can we tolerate acids in the presence of alcohols without totally protonating all the lone pairs, but we need them to make the carbonyl reactive enough. So this is the mechanism for addition of oxygen nucleophiles to carbonyls, whether they're ketones, aldehydes, esters. This is the pattern that we're going to see. So we have to protonate carbonyls in order to get this addition step to work for carbonyl compounds. And so let me go ahead and show you the intermediate you generate. We'll have two types of oxygen atoms attached there. Boys, those will do lots of things. The main thing it wants to do is it wants to push, the lone pairs here want to push this alcohol right back out, but the chemistry can become useful when mechanistically this does other stuff. So you can't isolate these continue to go on and do more chemistry. They either go back or forward, but you won't be stuck. There's no way to isolate these types of species, these tetrahedral intermediates. Now you need powerful acids to protonate carbonyls like this. If you were trying to get alcohols to attack, acids like sulfuric acid, hydrochloric acid, toluene sulfonic acid is one of the common ones we're going to see. So that's what we're seeing in this chapter. We're learning about how to get oxygen nucleophiles to attack carbonyls. So let me try to lay out what you're going to see in this chapter versus what you've seen in other chapters. I want to try to distinguish these classes of nucleophiles. Some of these we're going to learn about the bottom nucleophiles in this chapter. And in the last chapter, you learned about these top nucleophiles, hydridoborate reagents, organomagnesium reagents, organolithium reagents. That was the last chapter. The bottom part of these nucleophiles are coming here in chapter 21. And I want to put some quantification here on the relative nucleophilicity or basicity of these bonds. Basicity, I'll write nucleophilicity and basicity. They kind of correlate. These bonds are nucleophilic and basic. Let me go ahead and quantify those for you. Organolithiums that are, and really what's different here is whether this is sp3 hybridized bonds between carbon and lithium, or sp2 hybridized bonds, or sp hybridized bonds. There's a huge difference in reactivity between sp2 phenolithium versus sp3 butyllithium, right? It's the carbon atom here. We look at the carbon atom to determine how reactive is that atom when it's attached to a metal. So for sp3 hybridized Grignard reagents or organolithiums, or if you could make it an organosodium, that's at the top of our relative basicity scale. Next in line is when it's an sp2 atom like phenyl or alkenyl. That's not as nucleophilic, only 10 to the 42 on our scale. 8 orders of magnitude difference is a huge difference in nucleophilicity. And finally, we get down to these alkynyl type nucleophiles like alkynyl sodium or calcium carbide that they put in miners' carbide lamps. These are only basic to the tune of about 10 to the 25. This is log scales. These are huge differences, even though they look rather small. Finally, we get down to lone pairs on alkoxide, on oxygen atoms. Way less nucleophilic than all these carbon nucleophiles we've talked about. And the basicity keeps decreasing as we go in this order. A simple amine lone pair, a neutral amino group, that's only got a pK that suggests a relative basicity of about 10 to the 10th. We're going to learn in this chapter about amines attacking carbonyls, alkoxides attacking carbonyls, cyanide anion attacking carbonyls. That's about the same as an amine. And then finally, we get to the weakest of nucleophiles we'll be talking about, and it's 10 to the -2. So much less nucleophilic than these other classes of nucleophiles. You can see why we need to help oxygen atoms when they attack carbonyls. So this is going to define for us what types of conditions we need to get things to attack. So all of these reagents up at the top here, all of these reagents go through an addition mechanism that looks like this. Just something adds with no assistance to the carbonyl. But then finally down here with the oxygen nucleophiles, water, alcohols, in those cases down for those oxygen nucleophiles, we have to protonate the carbonyl in order to get the alcohol to add. You can't get efficient rates of alcohol addition to carbonyls without throwing in hydrochloric acid or sulfuric acid. So what that means is that when we do reactions of alcohols to esters or ketones or aldehydes, we have to put in a strong acid under those conditions. Strong acid, hydrochloric acid, sulfuric acid, toluene sulfonic acid. For these reagents, maybe above, I'm going to say alkoxide and above, you do not want any acid anywhere around. You want to avoid acidic conditions. You just want to avoid proton sources you don't want to protonate off your nucleophile and ruin it. So we avoid any type of condition that's acidic. And what you're going to find is in this chapter is here in this middle ground, it turns out, surprisingly, that we need mildly acidic conditions for addition of amines and cyanide to carbonyls. And so this is what we're going to spend the rest of this chapter in our book talking about, is these lower types of nucleophiles and why we need mildly acidic conditions and why we need strongly acidic conditions to get oxygen nucleophiles to add. So that's what this chapter is mainly about. Then we'll talk about a weird reaction they couldn't find a place for called the Wittig reaction, and that's what we're going to do. Okay, I know it seems weird to focus on this chapter because this is not going to be on our next exam, but it'll be on the one after that. So you may have a tendency to think, I don't want to study for this because I got to get ready for that exam. Okay, great. Spend the weekend working on the exam material, but don't let this stuff slide by, because if you don't stay up on the material, it's going to be hard to catch back up later. So work a zillion problems, keep studying for the exam. Thanks for tuning in to our Zoom lectures, and you guys have a great week and stay healthy and stay sane.